Modeling data using exponential functions. Right. Okay, so we've done all the characteristics of exponential functions. We've looked at the base. We've looked at the y-intercept. We've looked at what effect the base has and stuff. So, just going to kind of ignore this first little example. You can read through this, of course, but population data. So population data often follows an exponential growth pattern. So I've collected some Canadian population data from 1971 up to 2014. And so what we'll do is we'll go in, we'll enter this into our calculators. We'll take a look at it, see what the shape of the data is. So get your calculators out. Turn them on. Best thing to do is just to go second function and the plus sign. And number 4 is clear all lists. Okay, so we're going to go second function into the memory part of it, which is the plus sign, so second plus. Number 4, clear all lists. Hit enter, so it's done. We'll go into stat, edit, and in L1, so let's just pop over here for a sec. In L1, we're going to put the, that moved pretty quick. We will put the numbers 0 to 43. 0 to 43. You're going to have lots of data to work with. It's okay, we're in class, we can do that, right? I mean, you're not going to get that on a diploma, we're not going to give you 40. So L1, just put 0 through 43. Right? Then we'll worry about filling in.
Are you gonna make the 4 kids watching this video watch all of this?
Yeah, why not? You must suffer for lack of attendance.
Although most of the kids who lack attendance are gonna watch this video.
Likely true. But the rest of us can go through it at double speed, right?
And cherish this moment. We'll watch it next year.
Yeah. We'll have you in the background, Sam, telling us.
That's too much video.
Yeah. So we're going to 43, right? Oops. Maybe we should type 40 in wrong.
Casey Robertson to Student Services, please. Casey Robertson.
Commissioner Yanner, you screwed up.
Oh, no doubt. Multiple times. All right. So let's go fix that up. Well, that would be a mess up, too. 33. Oh, the 3 again. 33. How come? 33. 32. All right, so that's the easy part. Now, we put in the population. Right now, with all of us running it, as long as 5 or 6 of us agree, then likely we'll have the right numbers, right? And if not, and we'll also look at. All right, so I'll just leave the first 13 up, so you can just start entering them. So if you're doing this on your own, on a quiz, test, whatever, then you should be going back out and checking over numbers. And I'll show you. What I would do, or what I will do, just as part of a check. Uh, 24.20. So occasionally you should kind of look up and make sure that it matches. So number 9, yeah, 24.52. And number 10, 24.82. I got 11, which is 25.12. And here what I'll do is just scroll that up a bit. Let's go throw, say, 8 at the top. So. I'm at 11, 24.12, 12, 25.61, 25.4. So all I did was pull the data off of the StatsCan website and divide the numbers by 1,000,000 and then show 2 decimals, right? So that we're not, because you don't want to be typing in the exact numbers. Each line would have 7 figures on it. $28.04, $28.37. Almost halfway there. Hey, real data is painful, right? I mean, it's like no fake data here. All right, so scroll up to. Whoops, how did that end up back at the top? All right, there we go. 25, 29.61. 9.9. So on the diploma, you might be doing 6 or 10 numbers.
Miss 29.3.
It's okay. What do we got? Hey, 29.61. Okay, wait. What did I miss? 29. Oh, 29.3. So 20. Now then I missed something else because I've got this. Oh, I missed a 22. There we go. That's a problem. Yeah. I don't even know if I can insert a line. Apparently I can. 22. Okay. So now let me go back and clean that up. 22 was 28.68. Yeah. 23 is 29. 29.3. 29.61. So occasionally looking up and checking is a good thing. 30.4. 31.64. 31.94. 32.57. Whoops. All right, and let's get the rest. 36, 32.89, 33.25. Okay, so I've messed up 2 there. I'm going to leave them, right? Well, I'm going to have to come back and fix them, but. Okay. Because I just want to show you, okay, so what is it going to look like, right? Because realistically, this could be something you end up doing as a project, in post-secondary, or something along the lines of you're going to actually be entering 40 or 50 pieces of data or a couple of hundred pieces of data, right? And so you need to go back and check over, right? Like if it's for a project or something, or if you're doing this. So I can say, okay, my window, it was years since 1971, so 0 was 1971. And we were going up to 43, so I'm gonna go to 50. And we'll go by fives. That'll give us 10 ticks along the bottom, right? I mean, it really doesn't matter with the scale. If you've got it too small, you'll just see the ticks closer together. And here we're going from, what was our lowest value? Well, let's go from 0 to, okay, we got 35 million. Let's go to 40 million maybe. And remember, this is in millions, right? So the population is 35.54 million. And the scale for that, by fives as well. Okay, now if I want to look at the data, just the dots, the points, so we go to second function y equals, and we want to turn on the stat plot. Okay, and if you leave a stat plot on, but you've cleared your data, you're going to get this error invalid dim, right? It's invalid dimension. It just basically says, hey, you're trying to graph something and there's nothing there. Basically, everything just stays as the default. Okay, when you're doing a stat plot, and I'm just going to hit graph. And notice I can see, oh, okay, I think I have a couple of points that are out here, right? Because it's all kind of moving along there. Actually, it looks pretty linear at that point, right? Looks like it's a straight line. And so we may want to turn our diagnostics on and check that and see. But first, I got to fix those. So I got to go to Stat, Edit, and just pop down. I know they're further down in the table. And they're kind of going to stand out, right? All right, there they are. So 37 should be 33.25. And 38 should be 33.63. And just hit graph again. All right, looking good. Let's turn our diagnostics on. So I'm just going to quit out of the thing. Go. Oops, hold on 1 second. I want alpha D, and I got to do that twice, I think. No, what am I doing wrong? Oh wait, catalog. So second function catalog, and then alpha D, and we want diagnostics on. There it is. Enter, enter. You won't have to put your diagnostics on the diploma, right? You won't have to figure out what kind of regression to do. They'll tell you, run an exponential regression or something, right? So I'm just doing it because I'm curious, right? It looks like a straight line. So I'm going to go stat, calc. Let's run a linear regression just to see. I'm not going to put anything else in, right? I'm just going to let it do its stuff and show us the R squared value. Okay, so just say L1, L2. I'm not going to store the equation. Just want it to run it. R squared, 0.9986. It's pretty good. Stat, calc. Let's run a quadratic just for the heck of it. .9992, and then let's run the actual one, which is the exponential. So exponential is closer to the bottom of the list, so I just arrow up because you'll get to exponential faster. Okay. And I am going to tell it to store. So vars over to y vars, hit enter twice, so it puts y1 in there, right? And all we're doing is telling it once you've calculated it, calculate. 0.9978. It's lower than the linear, but this is an exponential. Okay, it is population growth, and population growth generally follows an exponential regression. And so we've got some numbers there, right? Y equals 22.1. Let's call it 22.20 and 1.011. Actually, I'm going to go to like 4 decimal places on this. So we got 1, 2, 3, 4. So 1.0, let's write this down here. So y equals 22.1978. 22.1978 bracket. Okay, that's our A value, right? A, and then we put the b in brackets, so 1.0112, 1.0112 to the x. Okay, so that's our exponent. That's what we get as a result of doing an exponential regression. Okay, let's graph it, look at it. You can see the line being drawn. It's kind of, everything's pretty tight together there, right? You'll see it pop out at the end in a second. So you can see that is a pretty good fit. Our scale has kind of just made it so it doesn't look very exponential, right? It's not curving up. So we could change that by setting the window. So what was our first value? What was our lowest? Anybody remember? Let's go look at it. Stat. Edit. So 21.96. So window. So let's say we went, the y value is from 20 to 40. 20. Even there, still looks pretty linear. And it's drawing in the graph. All right, so what does this tell us? Is this growth or decay? Growth. This gives us our initial population, right? The first or the starting. Now that's based on the model, not necessarily based on the number that's actually in the chart, right? So if I actually scroll back up, that's 21.96, and here it's 22.20. So this is our initial population, right? So in 1971, based on the model. And this is years after 1971. That was good. Years after 1971. Now, if we want the rate of growth, what we do is we take this, 1.0112, and we subtract 1 from it. So we know it's bigger than 1, it's growth. You subtract 1, you get 0.0112. That's growth as a decimal. Now usually we express it as a percent, so you take this and you multiply by 100 and you get 1.12%. So the growth rate in population in Canada from 1971 to 2014 has been a growth rate of 1.12% per year. That's the rate at which the population is growing. And in that time, it's gone from 22.2 million to 35 million. Okay, and that's over 43 years. So it's exponential growth. We would be told to run an exponential regression. Okay, we wouldn't. There's nowhere on the exam they're going to. I mean, they might give you 4 graphs and say, which of the following is the graph of a cubic or something, and they'll give you like a sinusoidal, an exponential, whatever, and ask you to choose. But when it comes to running a regression, if they want you to do one, they'll give you the data and they'll say run an exponential regression or run a linear regression, whatever type. Now, what did they have in here? Oh, wait. So this one had population growth, but this time from 1871. Basically, it's the census, right, which is done every 10 years. So this is giving data from 1871 to 1971, and the actual population, and then population in millions. And so we could enter those. We're not going to, right? They did it, so we'll just look and see what they got. But you could enter those into your calculator. Generally speaking, if I was doing that, I wouldn't enter the actual year number, right? Just makes for kind of ugly stuff. I would just say this is 0, 10, 20, 30, 40, 50, 60, 70, 80, 90, and 100, right? So it would be the years after 1871. So you can see the plot. This looks a little more exponential because you can see that there's growth, but it's also over a 90-year period, right? So I entered the numbers 0 to 10, right? So instead of putting 1871 and so on, right, you say that's 0 and that one is 10 into the list of the graphing calculator. Ran this, got an exponential equation somewhere. Okay, down here. So 2.668, 1.239. So what would the growth rate be there? So you go, okay, 1.239. Okay, I know it's growth, right? Because it's greater than 1. So we subtract 1 from it. We get a rate of 0.239. We want to turn that into a percent. We multiply by 100, giving us 23.9%. That's saying from 1871 to 1971, we had a population growth rate of 23.9% per year. A lot more growth. There's a lot of immigration. You guys all studied social studies, right? So a lot of immigration and stuff, and that. And, you know, we might have a bit less immigration now, and just more. It's just natural population growth. So determine blah blah blah. Use it to extrapolate. So on a graph. So here they're saying, assuming the population growth continues the same rate, the population in Canada would be about 54 million in 2011. Okay, well, we know that didn't happen, right? Because we've got the data sitting right here. That's 2014, 13, 12, 11. So in 2011, it was 34.34 million. So growth doesn't necessarily continue at the same rate. Hello? Yes. Sure. Okay. Bye. So one thing, anytime you're doing any of these models and you're going to state stuff like this, then you just say, if I want to use this model as a predictor, so if we want to take this, it's gone blank. Oh, there we go. Okay, so if we want to predict, if I can say what was the population, so we went to 2014, and I'm saying, all right, what's the population going to be in 2020? So what year would 2020 be? I was finding it handy to get the fingers out, right? So 2014 is 2014, 15, 16, 17, 18, 19, 20. Now it's 43, 44, 45, 46, 47, 48, 49, right? So in year 49. So we go here, we go second function calc, value. So I want the x value to be 49, right? I want it to be 6 years down the road in 2020. And what would the population be? Right, and it's saying 38.22 million. And we could say, well, when is our population if this continues? And remember, anytime, if you're extrapolating, if we're interpolating, which is reading in between numbers, so if I say there was population halfway through, 1982 or something, so I'm going to use 14.5 then, I can find. That's interpolation. That's going to be fairly accurate. Extrapolation says, you need to mention something about assuming the growth rate continues, or growth continues at the same rate, right? Because the guys, when they did it over here, hey, you're getting 54 million. So no, we're not, right? Not even close. So using this model, which may in fact be a little bit more accurate, right? Because it's got a fairly slow growth rate, 1% per year. When will we hit 50 million? So you go to y equals, you go to y2, and you say, well, the y is my population. I want to know when I hit 50 million. And it's at this point that you realize that your window's not big enough, right? We don't actually have 50 up there for y max. Okay, so we're going to want to go a little bit above, let's say 55. And I might have to take the years out a bit more. So let's go out to 60 years and see what happens. So first, it plots the data points, right? That's your scatter plot. Next, it's going to draw the regression line. You see it's starting to curve a little bit more here, right? It's like looking a little less straight. And x values, we have to go further out. Okay, I'm going to go to 100. So first, it's going to plot the points, right? And then it's going to draw the regression equation in, which now is starting to look a little bit more like a curved line than we had before, right? So if you're looking over a larger period, okay, now we can say, okay, second calc. So I need the intersection, right? I can say what x value will have that y value. So I'm just going to move along here painfully, slowly. And so it'd be 73 years after 1971. So 73 years after 1971. 1971. So what's that? 4. So in the year 2044, if, right, big if population increase, or population, yeah, the increase in population occurs at the same rate, then we will hit a population of 50 million in 2044. Right? We all know the zombie apocalypse is going to come on and wipe everybody out. I mean, a sudden drop off the graph there. Solving a problem. Okay, here, let's do this one. So, assigning an experiment to determine the cooling curve of water. Place the same volume of hot water, and this is a good thing, right? You want to know how long it's going to take my coffee or hot chocolate or tea or whatever to cool down. So she recorded the temperature of the water in each cup as it cooled over time, and her data for 3 trials is given as follows. Right, so we're just going to plug this into our calculator, right? Okay, so second mem, number 4, say goodbye to the 86 numbers we just entered. Gone. Good thing to do at this time is to go into y equals and just clear stuff out. Okay, so we go to stat and edit. Scooch this over. So time is going to be our x value, right? We're going to go 0, 5, 10, 20, 30, 40, 0, 5, 10, 20, 30, 40, 0, 5, 10, 20, 30, 40. So 0, 5. 0. 0. Okay, and then over to list 2, and so we've got 80, 60, 80, 69, yes, can't get it right, 69, 61, 40, 30, 26, 75, 66, 50, 40, 78, 68, 61, 44, 33, 20. All right, and nice enough not to point out that I messed up twice. 33. Okay, so first thing I want to do, anytime you do any of these guys, you've entered some data in there, look at the scatter plot, right? So the scatter plot is turned on, but my window isn't set. So window, okay, so the x's go from 0 to 40, right? So let's say 0 to, let's go to 50 by 5s, right? That'll allow us to do some extrapolation, right? So we could say, well, what would it be in 50 minutes then, right? Because they're only going to 40. And 0 to 100 maybe by 10s. And hit graph. And you'll see little clusters, right? Because each one is sort of the 3 measurements, right? At each of these times, we have 3 measurements, right? 80, 75, and 78. So they're all pretty close together. This is exponential, right? So we'll tell you run an exponential regression, which is stat, calc. Arrow up because exponential is closer to the bottom. L1, L2, store regression equation. So if you've got the older calculator, just go exp reg, vars, y vars, enter, enter. So it'll say exp reg y1. And if on this, we put in the y1. And then calculate. Got a decent r squared value. So it's y equals 78, let's go to 2 decimals, y equals 78.68, bracket, 0.97 to the x. And let's hit graph. So it'll draw the curve. Decent curve. Going nicely through about the middle of the blocks, or it's definitely hitting all of the blocks there. Is this growth or decay?
Decay.
Decay, right? Goes from Q2 to Q1 decreasing, but in our context, we're not going into quadrant 2, right? That would be negative time. That wouldn't happen, right? We would just be staying in quadrant 1. What's the rate of decrease? Okay, they're going to ask you, this is a common question. You get something like this and it says, what's the rate of decrease? So I'm going to give you 4 choices. 97%. I don't know, some other number. 3%. I can't just make these up. I got to be, all right, hang on. So, okay, 97%, 79%, 21%. Really? Question, right? So this is the equation you get. Rate of decay is 97%, 79%, 21%, or 3%. Hey. Well, I'm hoping you'll know when it's the real thing.
97%. Okay.
Okay, so it's 3%. And here's why. So when the b value is less than 1, we know that's decay, right? We know it's going down. At what rate? Now, if it's going down by 97%, then it would be like at 100, and then boom, it would be down at 3, right? So the way to figure out the rate of decay, you go 1 minus 0.97, which is 0.03, and then you multiply that by 100, which gives you 3%, right? So it's going down by 3%. Okay. Or you would see it as something like if, you know, there's let's say there's a winter clearance sale and they say 25% off. It's a $100 coat. So you got a $100 coat on 25% off. How much are you going to pay? $75, right? So if it was 25% off per week, then after the first week would be $75. The next week it would be $56.25, right? It would be 75%. You take 25% off again, right? So when you think of it, when I've got this, what it's doing is it's going, you know, if it starts at 100, then it goes to 97. So it went down 3%. Then it goes to whatever 97 times 0.97 is, right? Like 93 point something percent. So it just goes down by that amount. So with decay, it's a common type of question that gets asked on the diploma, right? Like what's the rate of decay, or the rate at which depreciation would be another word for it too, right? This could be the value of a car and it's depreciating. So if it's exponential growth, you subtract 1 from the rate because it's over 1, and then you multiply by 100 to give you the percent growth rate. If it's exponential decay, you subtract the b value, from 1, and then multiply by 100 to get the rate of decay. Okay, and then, okay, and that's what we were looking at, right? Now, then you get asked some questions about doing with that. Estimate when the water temperature reached 30 degrees Celsius. Okay, so our temperature is our y value. So we're going to put in a 30, and then graph. And the x value is time. So we go second, calc, intersect, And we basically just want to find what x value goes with the y value of 30. What's that called? Interpolation or extrapolation? Inter, right? Because we're in between the two data points. So 33.37 minutes, 33 minutes, 33.4 minutes, whatever the rounding is, okay? If I extend the window out, let's take the x out to 100 minutes, then, you know, is this thing going to go down to 0 degrees? Like, how cold is the cup of hot water going to get?
Very cool.
So let's say it's in the room. So we're in the room. So there's my water bottle there, and I had it filled with hot water. Or somebody has their coffee or tea or hot chocolate or whatever it is, and they let it sit. Then how cold is it going to get? Yeah.
Depends on the room.
Yeah, room temperature, right? It's just going to go down. So this model, again, it's not going to continue to 0, right? Not unless it's outside and it's 0. You know, and that's not likely what's going on, because things would cool down a lot faster. So the model is good for the length of time over which she's measuring, right? But then she's getting to the point where, you know, again, if we look at the data values, getting to the point where it's, well, 26 degrees, right? And room temperature is what? Like 20 degrees. Except in this room where it's like 18 degrees. We just didn't get any heat. So, you know, yeah, it's cooling at that rate, but at some point it's just going to level off, right, at room temperature. So it will no longer be cooling at that rate. And really, it's just the idea of keeping in mind that a model of cooling or a model of population growth, you're making certain assumptions, right, that the population is going to continue to grow at that rate. But that led us to 50 million people in, you know, 2011, and we don't have 50 million people. So regression appears to be a good fit. Your turn. No, we won't take a turn. We'll pass. In summary, key idea. So graphing technology can be used to create a scatter plot. When the scatter plot looks like an exponential function, then it is an exponential function. You use an exponential regression, okay? And we will tell you which regression to use. So it's only that one polynomial one, RFP, where I just said run them all and then choose one. An exponential function models growth when a is greater than 0 and b is greater than 1. The y values of an exponential function increase as you move from left to right, right? So Q2 to Q1 increasing. Models decay when a is greater than 0. A still has to be greater than 0, right? And b is between 0 and 1. Exponential decay decreasing as you go from left to right. And rate of increase, rate of decrease. If it's increasing, subtract 1 from the b value, multiply by 100, that's the percent increase. And if it's between 0 and 1, subtract it from 1, multiply by 100, that is the rate of decay, decrease, or what do we call it, depreciation. Exponential curve of best fit can be used to predict values that are not recorded. You can interpolate, so in between values. You can extrapolate going beyond the values, but be very aware if you're extrapolating that you're getting into unknown territory. And in the case of the cooling cup, you really got to watch out and say no, like it's going to stop when it reaches room temp.